Welcome back, students. This is the third video in a three-part series on alkene chemistry. In this video, we will take a look at halogenation, which is adding two halogens across an alkene, Halohydrin formation, which is adding one halogen and one hydroxyl across an alkene, and then dihydroxylation, which is adding two hydroxyls across the alkene. And then finally, something off tangent a little bit, oxidative cleavage. Let's get into it. Halogenation involves the addition of two halogens across the double bond. Now, the only halogens that are possible for this reaction are chlorine and bromine. If you try doing this with fluorine, it works too well. It releases too much energy, too much heat, so it is quite explosive and dangerous and not practical for the lab. On the flip side, if you try this with iodine, it is too inefficient of a reaction to get you any good products. So halogenation really is only for chlorine and bromine additions. So for example, if you had this alkene, you add molecular chlorine into this, two chlorine atoms will be attached to the vinylic carbon of that alkene. In the same way, if we add molecular bromine to an alkene, you will get a dibromo product. And it turns out the addition of the halogen will be in an anti-fashion, where the two halogens will be added in opposite orientation from each other. So let's go into the mechanism of this reaction. First, let's take a look at our reagent, the molecular halogen, and we'll take bromine for our example. So molecular bromine is a covalent bond, so you would think that it is a nonpolar bond, but it turns out because it is such a large atom and has lots of electrons, it is quite polarizable, meaning you can induce a temporary dipole. Especially if you have a nucleophile around, the proximity of that nucleophile will make one of the bromine more electrophilic and therefore more susceptible to be attacked by the nucleophile. And as we have seen in this entire chapter, our alkene is a very good nucleophile. So you can imagine the nucleophile attacking one of the bromine atom that is more electrophilic, giving us this carbocation intermediate. However, this mechanism does not fit well with our previous observation that the product of the halogenation is an anti-product. So whatever mechanism we propose must be corroborated with that fact. So as you can see, if you go through this mechanism via a carbocation, you can imagine that not only the anti-addition, where bromine attacks from the bottom, will occur, but because the empty p orbital also has a top phase, that the bromine can also attack from the top, giving you a syn product. And we don't observe any syn products. So because of that, it doesn't go through a carbocation, not quite. So what does it go through? So let's work this backwards. We already said that it's going to give us an anti-product, looking like this. What intermediate structure and mechanism could give us this anti-product? So the proposal here is that it goes through what is known as the bromonium ion, which is a bridge structure where you have a three-membered ring with two carbons of the alkene with the bromine as a third member and a positive charge on the bromine. Now, as you imagine, a three-membered ring is very strained, so it wants to be opened, so it's quite reactive. Since we have a bromide nucleophile flowing around, it can go in and do a backside attack, releasing that strain, giving the electrons from that carbon-bromine bond to the bromine atom, resulting in the addition of the second bromine atom. Notice that we propose using a backside attack of that bromide nucleophile. That is congruent with giving an anti-addition. Alright, so now back to this bromonium ion. So how is this bromonium ion created? So the proposal here is similar to what we said earlier, where the pi bond is your nucleophile attacking the bromine atom that is electrophilic, more partial positive, and then breaking that bromine-bromine bond. Except we add one more step where a lone pair on that electrophilic bromine also does a nucleophilic attack at the same time, so it's concertedly attacking the other vinylic carbon that is lacking an electron as the pi bond goes away, right? Originally, we would have proposed that to be the quote-unquote carbocation. And then finally, you can do this also from the bottom of that pi bond, giving us two different stereochemical pathway, and at the end, giving us the other products. So these reactions will produce two enantiomers. And so because of that, halogenation is also stereospecific. So the stereochemistry of the starting alkene will determine the stereochemistry of your product. So for example, here we have two very similar molecules. In fact, they are stereoisomers. One is cis-2-butene, the other is just the trans version. Now, depending on whether you use the cis or the trans, you will get very different products. For example, if you use the cis-butene, you will get these two enantiomers as your product. And when you use the trans-2-butene as your starting material, you will get this molecule. Now, if you rotate this molecule a little bit so that it resembles that of the top, you will find that it looks like this. Notice that these three molecules are all different from each other. The first two molecules on top are enantiomers. The one on the bottom is its diastereomer. Okay, and notice the one on the bottom doesn't have an enantiomer because it is a meso compound. So be very careful of designing your synthesis if you want to use a cis or trans, depending on what product you want to create. So we just discussed how to install two halogens across a double bond. Now let's talk about a very similar reaction called the Halohydrin formation. So we start with the same process here where we have an alkene, and if you react it with a molecular bromine or molecular chlorine, you will get our dihalogen product, right? Now this reaction only works if you do it under a non-nucleophilic solvent, like chloroform here. However, if you do this under a nucleophilic solvent, like water, you don't get these products. Instead, you get a similar thing, but instead of a second bromine being added, you will add a water molecule. And then the last step of removing one hydrogen will give you an alcohol. So the final product is a molecule where you have a halogen and an OH adjacent to each other. So how does this work? So let's go back to that bromonium ion. Remember we said that that was super reactive because it wants to open up, relieving that three-ring strain. Well, if you just have any nucleophile around, it will do. So if you have water around, water will be that nucleophile. And of course, bromide can also compete, but because water is a solvent, it is so much in excess and it's all over the place, it will outcompete your bromide. So you have some dibromo products, but mostly you will have this halohydrin product because the water molecule will outcompete the bromide ion as the nucleophile. Okay, so let's go over the mechanism in full. You form this bromonium ion where then it is attacked by water as your molecule in an SN2 fashion, so a backside attack, which explains for the anti-addition stereochemistry, giving us this intermediate. We just need one more step to remove that proton from the oxonium ion. And since we are in water, our base of choice will be water. So water does a proton transfer to give us our final product, the bromohydrin product, plus its enantiomer. Now, like I said, this can also happen with our chloro substrate. So if you have molecular chlorine with water in there with the alkene, you will form what is known as the chlorohydrin product. Now let's talk about the regiochemistry of this reaction. Let's see what happens if you have a non-symmetrical alkene where one side of the vinylic carbon is more substituted than the other. Where would you expect the bromine be added, and where would you expect the OH to be added? It turns out the OH will be added to the more substituted carbon, and the bromine, of course, to the less substituted carbon. And let's see why that is. Remember that in the first part of the mechanism, you react with the molecular bromine to form your brominium ion. Now, with the brominium ion, then you have your water doing the attack. It will attack on the more substituted carbon, and then the protonation step. So now let's go back to the step where the brominium ion is captured or reacted with water. How does water choose which side, which carbon to attack on? And the key here is in that brominium ion. So you see here that bromine has two bonds to the carbon structure, right? Imagine one bond disappearing. You will form a carbocation, right? Either on the left or on the right. Where do you think you would prefer a carbocation? The one on the left where you are tertiary, or the one on the right where you are primary? Which one is more stable? The tertiary carbocation, right? So because it is more stable, it has a lower energy profile, so lower activation energy. And so that pathway then will be more preferred. So again, we don't say that that carbon is a straight-on carbocation. We just say it has carbocation character. But you can use this reasoning as if it is a carbocation to explain why that is the preferred site of attack. All right, let's stop here and do a practice problem. So we have here this alkene undergoing reaction with molecular bromine in the solvent CCl4. So how do we draw our product? First, I draw out the linear part of that alkene that are horizontal. And then now I notice that this is where the vinylic carbons of the alkene were. And so each one of those will have a bromine attached to it. The one on the left already has a methyl group. I'm going to draw the methyl group out, and therefore the bromine must be back. Remember, this is an anti-addition, so if one bromine is back, the other bromine must be out. Okay, so that's one product that you will have, and then you may also have the enantiomer, where this time your methyl is pushed back and your bromine is brought to the front, and therefore the other bromine is to the back. Now let's see what happens when you do the same reaction, but in this case our solvent is water. Okay, so we start out with the same backbone. So remember, at this position, we have more substitution. So that's where your alcohol will be added. And then the other less substituted vinylic carbon as your bromine. So that's going to be one of your Halohydrin products. Of course, you may have the other enantiomer. This time your alcohol is to the front. And so therefore your bromine is a dash going back. Okay, let's do another practice problem. How about this one? So we have here this alkene, and then you add in molecular bromine in a non-nucleophilic solvent like dichloromethane. Can you predict what the product is and also draw the mechanism leading to the product? So what is of interest here? We have this alkene and this bromine, right? So you have your nucleophile and your electrophile. So let's draw that mechanism. Because I'm drawing the mechanism, I need to draw bond breaking. So I need to draw out the bromine-bromine bond also. The first step is the attack from the pi bond, breaking the bromine-bromine bond, and at the same time, a lone pair on that electrophile bromine also does an attack onto one of the vinylic carbons of the alkene. Alright, so I'm going to draw it as if the bromine was attacking from the top, so it's a wedge structure there, giving us our bromonium ion. Ooh, let's draw it in red. Now usually another bromide ion would come in and attack, giving you a dibromo substrate. However, remember when there's another nucleophile around, it will outcompete with that bromide. So you may ask yourself, well, there's no solvent in this that is nucleophilic, right? Dichloromethane is not nucleophilic enough to do this. There's no water around, for example. But notice we do have a nucleophile around. We have this alcohol group, which is very similar to the water. It has the same nucleophilic strength as water. So it will serve as your nucleophile to break open that three-membered ring. Now this will outcompete with a bromide ion because it is an intramolecular reaction, right? It happens within the molecule, so it's already there, so it's faster, rather than the intermolecular reaction between the bromide and your bromonium ion. So it does a backside nucleophilic attack there, breaking open your three-membered ring. And remember, the nucleophile will attack at the more substituted carbon of that bromonium ion. Okay, now to draw the product of this mechanism, let's count our atoms here. 1, 2, 3, 4, 5, and the oxygen being the 6th. So it's going to have a 6-membered ring where your carbonyl is there and your oxygen was there. Okay, so this was the vinylic carbon. It's still connected to the other vinylic carbon and then to the bromine atom. Notice I need to pay attention to my stereochemistry, right? This alcohol group must do a backside attack, and if this bromine was from the front, so this alcohol must have come from the back. So you can draw it with that stereochemistry. And then there was that last hydrogen that was still attached. And then lastly, it goes to our final product with a simple proton transfer. Let's just use our bromide ion as our base, which isn't correct, but makes it simple. All right, so there we have it. All right, so now let's be thorough and draw in the second product. Imagine that the bromine were coming from the back of the alkene and creating this stereoisomer of the bromonium ion. So when the alcohol does an attack, now it must attack from the front, right? So if it attacks from the front, then we have to draw this bond here as a wedge. And then so our second product looks like this. And so we do indeed get 2 enantiomers of this product. All right, let's continue with this pattern. Have you noticed in this video, we talked about first how to put two halogens across an alkene. Then we talked about how to put one halogen and one hydroxyl group across the alkene. So finally, now we're going to talk about how to add two hydroxyl groups across that alkene. In this reaction is the dihydroxylation, and by the name dihydroxylation means you're just adding two OH groups across that double bond. And it turns out there's two ways of doing this. There's the syn addition and there's also the anti addition. So we'll start off first with the anti addition. The anti addition, as suggests, will give us an anti-product called a trans-diol, and it's a two-step process. First, you have your alkene reacting with this reagent abbreviated as RCO3H. It's known as a peroxy acid, forming what is known as an epoxide. From the epoxide, you can either do an acidic or basic pathway to form a final product, but in this chapter, we will learn the acidic pathway. And with the acidic pathway, we'll form this trans-diol. So let's go over these steps in more detail. The first step is the conversion of the alkene to the epoxide. Okay, and so it starts with the alkene reacting with that peroxy acid. Peroxy acid is basically very similar to a carboxylic acid, except it has an extra oxygen in there. So that oxygen-oxygen bond is actually very weak and making this reagent a very strong oxidant. And so with those four concerted curved arrows, the peroxy acid will add an oxygen to the alkene, forming actually two bonds to the oxygen, giving us an epoxide and the byproduct. And as you can see here, an epoxide is basically a structure that's very similar to the ones we've seen before in the bromonium ion. Right? It's a three-membered ring. Instead of bromine atom, though, it is an oxygen atom as your third member. So some common peroxides you may come across are the peroxyacetic acid and the MCPBA, or metachloroperoxybenzoic acid. Okay, so know these two reagents. So starting with our epoxide here, if you do this under acidic condition, it will get protonated. It needs to get protonated first in order to break open that ring, because if it wasn't protonated first, if you break open that ring, you would leave with an oxygen with a negative charge. So once it is protonated, since you have water as a solvent around, water will act as a nucleophile to open up that ring in an SN2 backside attack, so giving this anti-addition of the water molecule, which again is a charged species, so we want it to be neutral. You just have to do one more proton transfer step. And since we have our water in hand, that will be our base to remove the proton. All right, giving us our final product, the trans-diol. Again, since the epoxide can form from the opposite face of the alkene, you will also get your enantiomer. Now let's go back to this structure, this protonated epoxide. And I've referenced it a few minutes ago, how it's similar, very similar to other structures we've seen in this chapter. Right? It looks very similar to a bromonium ion, and it's very similar to this mercurinium ion. So notice all of these three structures have that three-membered ring, so a very strained ring, so it's very reactive. Plus, it also has this formal charge. So once you open that ring, it will relieve that charge, yet again another driving force for its reactivity. And also they all prefer backside SN2-like attack, giving us our anti-products. Alright, now let's move on to syn dihydroxylation, where we will add two alcohols on the same phase. And so how you will do that is using osmium tetroxide here, OSO4. It will do a concerted mechanism with the alkene, giving this cyclic osmate ester. Notice that the two oxygens bonded to the vinylic carbons are on the same phase, and that's because of the previous concerted mechanism where both oxygens are added at the same time. Since they're added at the same time and both oxygens are from the same molecule, it must be faced in the same orientation. And as a secondary step, you can reduce this with sodium sulfite, Na2SO3, or sodium bisulfite, NaHSO3, to give us our final product, the cis-diol. So it turns out osmium tetroxide is quite expensive and also very toxic, so we want to avoid using too much of that. But because it's being consumed in a reaction, we would need a large amount of it. So instead of consuming it, we would like to regenerate it, making it more of a catalyst instead. Right? So you can add what is known as co-oxidants to regenerate that osmium tetroxide. So one of such is called NMO, also known as N-methylmorpholine N-oxide. So that, again, is just a co-oxidant that will regenerate your OSO4. So you can get away with this reaction by using a catalytic, a very small amount of osmium tetroxide. Another co-oxidant you can use is this tert-butyl hydroperoxide. And both of these will give you pretty good yield in your syn dihydroxylation. Another reagent that one could use is using cold potassium permanganate. And then you would do this under basic conditions. So I won't go over the mechanism here. You are not required to know it, but just add these reagents into your toolbox. All right, so now let's do a practice problem with dihydroxylation. If you had this alkene, how would you draw your product if it was treated first with MCPPA and then with acidic water? Let's first draw our backbone. Remember, it is a dihydroxylation, but in an anti-fashion. So if it's anti-fashion, the first one could be back, and the second one will be forward. So we have this, and we have this. All right, so let's do one more. This time I'm going to draw my alkene as flat and not diagonal, just to show you the difference. Okay, so the backbone looks like that. So it's going to add the dihydroxyl group in an anti-fashion. So one looks like that, and the other looks like that. And of course, the other guy, one going back, the other one going forward. Okay, make sure that these are not meso compounds. If they are meso compounds, then it's only one product. Let's suppose you did the same reaction now with osmium tetroxide and a co-oxidant NMO. What would you get? Remember, it is a syn addition, so you will get this product and this product. But notice, if you flip this molecule 180 degrees like a pancake around, you actually get this molecule. So these aren't actual enantiomers, but they are identical to each other. And you could have noted that because it does have this internal plane of symmetry. So this indeed is a meso compound. So its enantiomer is actually itself and only one product. Okay, so we made it to the last reaction of this chapter, and it's at the end of the chapter because it's a little bit different from the rest of the addition reactions we've seen, and that's oxidative cleavage. So this reaction is a two-step process where in the first step you add ozone, O3, followed by a reducing agent like DMS or zinc in water. So what happens is that you will cleave that pi bond totally in half, and then adding a carbonyl each to both of the vinylic carbons. Can you imagine that? All right, so here's what the products would look like. All right, notice this bond is broken here. And so this vinyl carbon, just add a double bond to an oxygen will give you this. And then again, this bond was broken. So this vinyl carbon, just add a double bond and oxygen at the end to give you this. So in this case, you get a ketone and an aldehyde. Notice that you're adding a carbonyl to both ends. So regioselectivity is not an issue here. And stereospecificity is also not an issue here since we're not going to create any chiral centers. So I'll go over the mechanism, but again, I won't test you on it. So our star reagent here is the ozone, and ozone exists in resonance-stabilized structures like so. So you have your alkene that does a concerted mechanism with the ozone to form this ozonide called molozonide. It further rearranges, breaking apart in two molecules, and then finally rearranges again to give you this ozonide. Notice that this was your vinylic carbon and this is your vinylic carbon. In the last step, you will add a mild reducing agent to give us our final carbonyls. All right, so let's do a practice problem with this one also. So the trick here is to notice where the alkene is and then get your eraser out to erase that double bond. And then at the end of those bonds, just draw in your carbonyls. So one looks like that and the other one looks like that. And then you just have to make it prettier. So let's count how many carbons should we draw as our backbone. So that's 6. Now stereochemistry is important when you redraw this. Notice that at the second carbon we have a methyl group there that makes it a chiral center. Since in our previous structure it is a vertex pointed up, I made sure that in our product the vertex is also pointed up when I draw in that wedge. And then you can also double check by assigning stereochemistry. We'll do that at the end. But let's now finish up this molecule. So at the first carbon you have your carbonyl, and at the 5th carbon there's also another carbonyl, and so it looks like that. So on the left hand side you have an aldehyde, on the right hand side you have a ketone. Alright, so let's go back and check if we drew in the chirality correct. So in that structure the configuration is S, And in this structure, the configuration is also S. Because of that, we have drawn it correctly. Let's suppose you didn't draw it like this. Let's suppose you start your zigzag in the opposite direction, where your vertex is pointed down. And then how would you draw this carbon here? Notice that maybe you thought, okay, so it was wedge, so I'm just going to draw in the wedge. And now let's double check the stereochemistry. You would notice that the configuration is actually R. So that's not the correct drawing, right? Which is a simple fix, because if you have R and you want the opposite, then you just have to change the wedge to a dash. And that makes it an S. So both these structures here are correct product, just make sure you have one of them. All right, let's do another example of oxidative cleavage. This time, maybe the reverse perspective. If you were given the product, can you delineate back what was the precursor alkene? So notice we have 4 carbonyls here. So that means it was broken up from 2 alkenes. And because these carbonyls are in the same molecule, so that means that alkene was part of a cyclic system. So if we count the carbons, starting from the carbon of the carbonyl to the next carbonyl's carbon, we can see where the connection would have been. So let's go with this one here. It's 1, 2, 3. That's too small of a ring, so let's keep on going. 3, 4, 5, 6. So that seems like a perfect ring, right? 6 carbons in it. All right, so that's one set of the vinylic carbons. Now let's find the other set here. The other 2 carbonyls we have is 1, 2, 3, 4, 5. Okay, 5 is good, so it comes from a 5-membered ring with the alkene in it. So let's just number it. We can go ahead and draw in a 6-membered ring. Let's label the numbers to help us out here. So we know that carbon 1 and carbon 6 are doubly bonded, so we can draw that in. And now let's number the other guy. So since we have 6 already, let's go with 7, 8, 9. We know that carbon number 3 and carbon number 7 are attached. And how many carbons is that? Remember, it was 5, right? And we know that that 5-member ring includes carbon number 4. So there you go. And remember, our double bond comes from carbon number 3 and carbon number 7. So that's our alkene precursor that underwent ozonolysis followed by dimethyl sulfide reduction. Okay, so that wraps up this chapter of alkene chemistry. In this chapter, we learned a whole ton of reactions with alkenes. So at this step, I would highly recommend you do flashcards. And the flashcards should include things like the reagent, and whether if it is regioselective or not, and what is the regioselectivity, and whether it is stereospecific or not, and what is the stereospecificity if it is. So having flashcards now will help you as we move on in organic chemistry. You will be adding more and more reactions to your knowledge library.